Good morning. Welcome everyone to another sessions of the Data Science Summer School. My name is Hui Dang, and I'm the manager at our lab here at the Hertie School. The Data Science Summer School is our annual effort to contribute to the open source communities by opening up scientific learning, specifically data science, for the general public. And we are very happy to see so many of the audience coming from different countries, industries, and disciplines joining us here today. I think I counted 50 different countries or all the regions that you are coming from, which I think is quite amazing. And our summer school is made possible by the generous support and funding from the Hertie School and the Discrete Foundations in Germany. And I'd like to thank them for the continuing support. Our session today is Statistics and Probability for Data Science, which will be held by Dr. Nicholas Nushkin. And he's currently a lecturer in mathematical data science at King's College London. Before that, he also worked at the Alan Turing Institute and also at the University of Potsdam as a postdoctoral researcher. His research interests lie at the interface of computational statistics, machine learning, and the mathematics of stochastic dynamics and interacting particle systems. Nicholas, the floor is now yours. I hope everyone will enjoy the session today. Thank you very much.
Hello, everybody. Sorry, there's still a little technical problem. Sorry about that. Okay.
Dashy Checkle entered the waiting room. Close, admit, view. Press CMD plus U to manage the waiting room. 2 people entered the waiting room. Close, view. Press C.
Really sorry about that. Can you hear me? Because I had to now mute the.
Yes, we can hear you.
The computer. Okay.
I think it's all right, Nicholas. We don't hear any more notifications from the iPad.
Okay. Yes. So apologies for this delay. Okay. Yeah, apologies again for the delay. It's really a pleasure to be here and to see you all participating in this summer school. Thank you very much for inviting me, and I hope you will enjoy the lectures. So this lecture is about an introduction to probability and statistics. And one of the most important things, of course, is to ask lots of questions in the lecture. So if you've got a question, then please do enter it in the chat. And I think we are going to try and make it as interactive as possible. Okay. So let me arrange this. Okay. So the main topic, of course, today is randomness. And I don't think it needs a lot of motivation. Randomness shows up everywhere, and certainly in statistics and machine learning, data science, when you want to analyze data, any kind of phenomena that you're interested in. We can discuss where randomness comes from. Sometimes it is inherent in the situation. So, for example, in a casino, of course, the outcome of a game will be random. That's really the essence of a random game. There's radioactive decay. We can discuss whether this is really the same, where the randomness comes from, and there are, of course, philosophical components to all these questions, coins, dices, and so on. We are going to ignore most of the philosophical components today and focus more on the mathematical structure, which allows us to circumvent many of these questions. Okay, so there is inherent randomness. There's often randomness associated to uncertainties. So there's just things that we don't know. For example, about models that we use. Unknown quantities. And then randomness can also be used to describe errors. So what if a measurement device in a physical experiment isn't accurate? Or what if we perform a study in a sociological study and some things about the procedure in which the data is collected is in fact not perfect, right? So measurement devices, oops, let's write it like this. Okay. Yeah, there is a philosophical component to all of this. As I said, where does the randomness come from? Is maybe the world deterministic, determinism, quantum physics? But this is not going to be part of this course, as I said, right? The mathematical framework that we are going to discuss will allow us to more or less ignore these issues. These are interesting issues by themselves, but today we are going to mainly concentrate on how to calculate with probabilities and how to analyze data. Still, sometimes it's convenient and necessary to think back about the question, where does the randomness in fact come from? Okay, the mathematical framework allows us to circumvent these questions. Okay. If you want to study more, I would encourage you to have a look at the following book. There's a lovely book by Chan, which is called Introduction to Probability for Data Science. Oops. I will give some pointers during the lectures to this book, and also provide some more suggestions for further reading, probably after the lectures, I guess, on the website, containing lots of exercises. Yeah, you know, it's always good to do lots of exercises, practice what you learn. Okay. Or maybe one that I'd also like to highlight is the book by Downey. So that's a very computational book. Most of the examples, or all of the examples, are in fact written in Python. So if you don't like mathematical formulae, you can look at the code, probability and statistics, probability and statistics. For programmers. Okay. Yeah, no questions yet. Okay, there's many ways of teaching probability and statistics. I decided to do something a little bit non-standard. We are going to focus mainly on examples, on intuition, and somewhat less on the formal theory. You can then look into the literature, or maybe ask me later if there are particular questions about it. And we're going to build up our thinking in two ways. So there's going to be part one, and it's going to be about simple random variables. We're going to discuss what this means, although this is not a very technical term. This is not a very technical term, and it is in some sense not very well defined. So it's not a very well defined concept, but I feel it helps to get yourself acquainted with probability, to think about it like this. So this is not a very well defined concept, but we are going to see what it means. So for example, throwing a die or throwing a coin and looking at the number on the die or whether the coin shows head or tails, this is going to be a simple experiment, right? Because only one source of randomness is involved. If we then consider, for example, we throw two dice, or we throw a coin repeatedly, then you can think of it as there's a more complicated situation which is built from simple ingredients. And so we are going to, in part two, use the simple random variables as building blocks to build up more complicated random situations. Complicated random variables. Okay, this approach towards probability is slightly non-standard because in the general theory that encompasses everything, there is no distinction made between simple and complicated random variables, and everything can be explained with a really unifying framework. Okay, but today we are going to hitchhike our way up in this way. And throughout, I'd like to we are going to discuss a few applications in data science and statistics. All right. So let's start with part one. Simple random variables. I think the best way to start is maybe through examples. So let's start with a few examples. Oh, no. Okay. So the first example, maybe the simplest example in the whole of probability, is flipping a coin. And the outcome can just be two things, right? We can have either heads or tails. So maybe I'm going to use a little bit of color here. Flipping a coin, outcome, heads or tails, or 0 and 1, or -1 and +1. We can discuss whether heads and tails are both equally likely. Is it a fair coin? Is it an unfair coin? Fair, unfair. Sometimes we call it biased or unbiased. Second example, roll a dice, roll a die. Possible outcomes. Okay, there's different dice, but let's think about a standard die where the outcomes can be any number between 1 and 6, integer numbers. It's not possible to get a 2.3 on a die, at least not on this die. And then we can have something a little bit different, right? We can say, for example, choose a point between 0 and 10, or between some other numbers, right? Between 2 and 5, but let's say between 0 and 10. Oh. 0 and 10, uniformly at random. So what this means is that here is 0, here is 10, and we pick any number between these two numbers. This can also be, for example, so here would be 5, this could be 3.5, or this could be pi, or 7.88901, right? So any number between 0 and 10 is allowed. And we can think that we want to choose this number with equal probability. So each of these numbers should be in some sense equally likely. We're going to discuss what this means. Yeah, you already see that there is some distinction right here in this example below. So in this example, there's infinitely many different possible outcomes. So the outcomes in this situation, impossible to write down, right? Infinitely many. Okay. So we can, maybe I'm going to change it a little bit. So that's situation A, uniformly at random, right? So uniformly, this refers to the idea that all of these numbers between 0 and 10 should in some sense be equally likely. But we can do different things, right? We can say something like, so choose a point between 0 and 10. But only take integer values. So then we are in a similar situation as before with the die, right? Only that we've got now more outcomes. Zero, 1, 2. We can also discuss whether 0 and or 10 should be included, right? And then maybe the last interesting modification of this would be choose a number between 0 and 0 and 10, but so that larger values, so maybe values closer to 10, are more likely than smaller values. So maybe with a high probability likelihood, we haven't really defined what this means, right? But I guess we've got an intuitive understanding what it means to have a higher likelihood for larger numbers, so that larger values are more likely than smaller values. Okay, I put this here in quotation marks because it's not really clear what we mean, right? But I think in this introductory examples, we can just, let ourselves be guided by our intuitive understanding of probability. Okay, what other, like 2 more situations that we can think about? Let's think about darts. Right, we can think that where the dart hits the circle, we can think of it as random. Random point in a disk. Then again, we can think about different probability distributions. We're going to think about probability distributions later, but maybe it is more likely to throw the dart into the middle of the disk, or maybe it's more likely that it hits the disk at the boundary, right? So that's maybe a modeling assumption. Yeah, and then the last thing that we can maybe discuss is temperature tomorrow in Berlin. I don't know, what's the temperature today? So we can think of this as involving randomness. We don't really know what's going to happen, and so we might think there is randomness involved in predicting the temperature. So that would be a number, or we can think, is there going to be rain or no rain? Right, so that's the scope of the first part of these lectures. Each of these situations involves essentially a single source of randomness, right? So we don't have any kind of complicated situations where we've got many dice or a die and a coin, and there's no interaction between different sources of randomness. The second part will be about randomness and interaction, right? So what happens when 2 or many different sources of randomness interact. Okay. So we are going to become a little bit more rigorous now, or a little bit more formal, and introduce a little bit of terminology. It's not very complicated, just so that you've heard it. So all of these are called experiments. Okay, of course, it's an everyday, it's a word that is used in everyday language, but in probability theory, it has a well-defined meaning. I see there are some questions in the chat. Let me finish this point, and then I'm going to answer to the question. So all of these are called experiments. Right, so roughly speaking, this is a procedure with a random outcome. With a random outcome that can be recorded, let's say. Okay, we're not being very precise or very mathematical, but I just wanted you to have heard the term experiment. So what is in the chat? Should I answer to these questions, or Hui, are you gonna take care of it? I should, so the screen should be bigger. Notebook screen is very compact.
Nicholas, you can answer them whenever you want. I will try to also.
So yes, we are going to touch on common questions and pitfalls, and I hope it's going to be applicable for interview processes. So is the screen okay, or should I change anything?
I think it looks okay.
But Nicholas, the screen.
Okay, let me just continue for now, then we are going to see what happens. Okay, so that's the first term, right? Nothing very complicated yet. We now want to describe these experiments, and we are going to need two concepts. Yeah, we are going to need, we are going to talk about two concepts, two terms, let's say. One of them is called random variables. I've already started using it, right? And probability distributions. So these are two concepts that can be used to describe in a mathematical way the experiments that we've discussed so far, right? Remember the coin, remember the die, remember the darts, the temperature, right? And so these two things are central notions to describe randomness. So let's do it. We start with random variables. And okay, it's also not very complicated, but I want you to have heard this word, and it's necessary to know it, just roughly the meaning of it. So it's a quantity or an object whose value or realization depends on chance, right? So it depends on randomness. Or we can say it is random. So the main focus is here, just fixing the idea that this can be, typically this is going to be a number. So for example, if we go back to the example, rolling a dice, rolling a die, so I always confuse it. Let me just check in the chat. Okay. So in this case, the random variable, usually a random variable is going to be assigned a letter or a symbol, right? So we can write 1 x, so that's the random variable. And okay, you know, in mathematics we've got normal variables, right? So deterministic variables, deterministic objects that are often described by a letter or by a symbol, so x, which can be 1 or can be any number or can be anything more complicated. So you had vectors and matrices, for example, yesterday. And the difference here is, of course, that this can be random, right? So here we have got 1, 2, 3, 4, 5, or 6, depending on randomness. Right, we can also have a little bit of a more mathematical notation. Don't worry, it's just notation. More mathematical notation. So we say that x is an element of a set like this. Okay, there's no big difference. It's just about notation, and it's about the idea that in probability theory we can have random variables and they are different from the usual variables in that they can be random. So they depend on randomness. As an aside, so this is when you want to learn more or read more, the notion of dependence on randomness, this can be made very precise. And the way this is made precise, this is at the heart of rigorous and axiomatic foundational development of probability theory. But we are not going to go very much into this, but I'm just going to mention it. Oh no, what's this? The notion of depends on chance can be made very precise. And so usually, and so the way this is done is when you say that something depends on something else, in mathematics, that's usually done using a function. So in precise terms, a random variable is a function that maps the so-called sample space. This is a little bit difficult to get your head around in the first place. Sometimes these sample spaces are quite abstract and in some sense hidden in the background. Okay, in this case, this would be a random variable. Now, this is sample space. Okay, so this is just, if you want to learn more, read a little bit more about the foundations, about the axiomatic approach towards probability theory. You can read it, for example, in Chan chapter 2. Okay. Yeah, this looks okay. No, what's happened now? Okay, perfect. Okay, so we've got this. This was actually example 2, rolling the dice, rolling the die. Let's think back about the coin flip. In this case, the random variable, again called x, could be either heads or tails. Or again, in more mathematical writing, heads or tails. Okay. Then what else did we have? We had uniformly at random between 0 and 10. So here, again, it's a little bit more difficult to write down what x can be, but x would be a number between 0 and 10, and yes, it is random, right? Now that we are here, notice that, so we already discussed this a little bit, but notice x can take infinitely many values, right? So this is in contrast to the experiments that we had before. X can take infinitely many values. And this observation leads us to our first distinction. So we are going to structure our part 1, at least starting from now on, in discrete random variables and continuous random variables. Continuous random variables. Okay, I hope it's kind of intuitively clear by now by the examples what we mean. So in the case when the random variable we are talking about takes only finitely many values, then we talk about the discrete random variable, right? Discrete means pretty much the obvious, the opposite of continuous. So something that takes the geometric intuition is that the possible outcomes are at distinct points which are not sort of smoothly connected, right? So this would be, for example, so we had examples 1, 2, 3b, and 5b. And to be a little bit more precise, we could say the random variable takes only finitely many values. So for example, the die, think back to the die. The outcomes are 1, 2, 3, 4, 5, 6. So these are three. So these are six finitely many possible outcomes, right? The random variable that takes these outcomes would be called x. Okay, maybe I'm going to make a little footnote here. It's not technically completely correct to say this or countably infinite. But to understand this, you need to know what the word countably means in this setting. And we're not going to really worry about this distinction. Neither do we need this distinction very much in this course, and also not in data science in general. It's not very important. Okay, so that's discrete. Now continuous is, of course, in some sense the opposite. So we had examples 3a and c, so where we took some number between 0 and 10, but without the constraint that it should be an integer, right? It could be 3.5788891 and so on. Okay. So the random variable takes, okay, and now we've got another weird word that we are going to ignore. So it's uncountably infinitely many values. If you prefer to think in pictures or geometrically, then you can think, okay, discrete this looks like this. Okay, imagine this is the axis or the space in some sense in which the random variable x can take its values, and the red points are the values that are possible. In contrast to this, let's look at the continuous case, continuous random variable. So again, we've got this little space here. And maybe the random variable can take all the values in this interval. So that would be continuous. Okay. Okay, looks good. Chat looks good. Okay, let's make another remark. So usually, certainly in this course, all of the random variables take numerical values. So we're talking about numbers. Random variables take numerical values. So, but the general framework of probability theory is very general, right? Almost anything can be random. And so we had, of course, an example already, right? Tomorrow it rains or it doesn't rain. That's not really a number. But the framework is very general. So let me write this. So almost anything can be random, right? Oops. Oh, yeah. Okay. So you could, for example, have random words, random sentences, random graphs, random geometrical pictures or constructions. So for example, if you've got a biological or molecular reaction, and then maybe there is going to be, so the molecule is going to change in certain ways, or there's going to be a new molecule. Then, for example, with some probability, you could have a chemical something that looks like this, and then with some other probability, it looks different, right? So these are not numbers, these are more general objects. And in principle, we can reason about those with probability theory as well. But in this course, we're going to think about numbers because it's, of course, easier to begin with. Sorry, what's happened to my... okay. Okay. Yeah.
Mate Grados entered the waiting room. Close, admit, view.
Sorry about that. Okay. Think chemical reactions. Okay. Okay, this was the first important concept that we had, right? Random variables. Are there any questions about this at this point? If you've got a question, I think, can you run through the 3C example once again? Yes? Let's do it. So the example 3C here, right? So the idea was that we choose numbers between 0 and 10. And so we are going to be much more precise. There will be more examples of this style later on in the lecture. But for now, I just wanted to convey the intuition that the probability distribution, which we are going to discuss next, can be different even though the outcomes are the same, right, in some sense. So maybe we compare example 3a and example 3c. So example 3a was the idea that we choose a number between 0 and 10 uniformly. So all of these numbers have in some sense the same probability, right? So maybe this would mean getting a number between 0 and 5, so smaller than 5, and getting a number between 5 and 10 would be equally likely. But we can change this, right? We can consider the situation where it's far more likely to get a higher number. So it's maybe far more likely to get a number that lies between 5 and 10 rather than a number between 0 and 5. Is it kind of clear? So there's not more sophistication at this point. What would be the notation of the event 3C? So events, we haven't really talked about events yet. We're going to talk about events later. It's called an experiment, right? And the notation is not yet, yes, so the notation is not yet different because we are just talking about random variables at this point, right? So this is actually very nice. We can make the transition very nicely here. So both in 3a and 3c, the random variable x takes values between 0 and 10. But what we change between 3a and 3c is the distribution, right? The probability distribution with which these values are attained. So maybe if it's I'm going to continue with these probability distributions, and then if it's unclear, then maybe ask again. Okay. Thank you so much for the questions. Okay. Okay. So probability distribution. Remember, first important concept, random variable. Second important concept, maybe I'm going to make here 1. Oh yeah, we have got 1, random variables, first important concept. Second important concept, probability distributions. Okay, let's start with the rough definition. Roughly, this means this assigns to every possible outcome a probability. Right, so far we've only talked about outcomes. Now we are talking about how likely is such an outcome. So this is an assignment, assigns to every possible outcome a probability. Okay, what does it mean, probability? Of course, I guess we kind of know what probability is, right? But in our setting, this is going to be a number between 0 and 1. Maybe I'm going to use a green. Let's use green. A number between 0 and 1. So when I say between, 0 and 1 can be included. Or equivalently between 0% and 100%. Okay, that's the rough idea. Let's make it a little bit more precise. And at this point, we go ahead and make our distinction between discrete and continuous random variables. So let's start with discrete random variables. Discrete random variables. Okay, and yeah, let's start with the coin. Let's start with the coin example. And so the probability distribution, if the coin is fair, right, if it is unbiased, if heads is equally likely, has the same probability as tails, then we would write something like this. The probability that we get heads is 1/2 or 50%. And the probability of tails is also 1/2, 50%. Or we can have something else. So this would be a different probability distribution. In some sense, we could think of it as being the same random variable, but having a different probability distribution. So biased coin, maybe if you want to trick somebody, you can use such a coin and base your bets on them. So the probability of heads maybe is only 1/4, 25%. Okay, if the coin is loaded, as they say. So if it's an unfair, somehow prepared coin, maybe 25%. then the probability of tails would be 3/4. Okay, simple example of a probability distribution. Well, my computer freezes. Okay, so this was the coin. Let's look at the die. So the probability of 1 if the die is unbiased. So if each of these faces, each of the numbers occurs with equal probability, then these probabilities are all the same. Okay, they're all the same, so they're 1/6. Don't worry, so these were just examples. We're now coming to, I hope it's kind of intuitively clear, but I'm going to sort of take these examples and record a few observations about them, right? And these observations can be then transformed into axioms, or could be transformed into axioms. We're not really going to discuss this here, but if you want to study probability theory formally with rigorous foundations, then this would be a good place to start. So we are going to make some observations about these examples. And okay, can be turned into axioms, so into a formal structure that describes probability theory in a mathematical framework, right? We're not going to really discuss this in a lot of detail. But okay, what we observe are a few things. So these observations, right? So let's start with the first one. For every outcome x, right? So here we assigned to every possible outcome a number. So this is an outcome, heads. This is a value that the random variable can take, and we assign to it a certain probability, and the probability is between 0 and 1, right? 1/2, 1/2, 1/4, 3/4. So that's what's written here in more formal writing. Okay, let's translate it into a sentence into a sentence in English. Probabilities are numbers between 0 and 1. Okay, included. We are going to discuss a little bit about interpretation, but of course, already now, I hope it is clear, if the number is bigger, then somehow the likelihood of this outcome occurring is higher. And in particular, if it's 0, then in some sense it's impossible. And if it's 1, then it will for sure happen. Okay, so that's the first thing to notice. And the second thing is, if we sum, I hope that's okay, this notation. So this means we sum over all possible outcomes. Then we have to get 1. So just to explain this notation, for example, if we have outcomes x1, x2, and x3. So this is just notation, right? We could say that heads is x1 and tails is x2. So it's just a renaming that we do here in the formula. Basically, we introduce this index I to write it concisely in this form. Then this means P of x1 plus P of x2 plus P of x3. So the probability that x1 happens plus the probability that x2 happens plus the probability that x3 happens, this should add to 1. Okay. Let's write a sentence. The total probability is 1 or 100%. Okay. Yeah. As you can see here, I already did it. Yeah, because I'm used to this. But I guess many people are used to this. So if we add 1/2 and 1/2, then we get 1. And here 1/4 and 3/4 also together give 1. So if we, in particular in this easy example with the coin, if we specify one probability, so for example the probability of getting heads, then already the other probability we can just compute it by adding up to 1. Okay. And similarly here in the dice case, we've got 6 different outcomes. If all of them have the same likelihood, the same probability, then as these have to add up to 1, then each of them must have probability 1/6. Okay. Okay, so maybe this last comment is worth recording. That's not always true. So if all outcomes are equally likely, so for example, in this case, we would call the coin, for example, fair or unbiased coin or dice. Then the probability of any of these outcomes has to be 1 over the total number of outcomes. Okay, this just follows from the fact, again, that they have to add up to 1, and if all have the same value, then that's what we get. Okay. And this is in some sense often connected to symmetry of a problem, right? If we don't have a reason to believe, for example, that one of the, like the die is symmetric, it looks the same from from every angle, so every face should be equally likely to be on top after a throw. And so by this symmetry, this can often be argued. Okay. This is related to the concept of symmetry. Okay, let me check the chat. It's been 1 hour. I agree. Let's make a break. Yeah. So are there any questions until here? Doesn't look like it. I would suggest we make a short break until, let's say, 10, 12. Well, I'm going to take this question first. So could we say that the more... Okay, so that's a very interesting question. The idea of how... Sorry about this. So Juan asked the question whether we can say something about how random is an experiment. So for example, if the coin always lands on the same side, then in some sense it's not random at all, right? We always get the same. And in this case, the random variable would actually be a usual deterministic variable. We are going to talk about variance later, and in this setting, we are going to make the idea of how random something is more precise. Okay, that's a very nice question, though. Thank you so much. Okay. To what extent are we going to dive into probability and statistics today? To some extent. So after the break, we are going to talk more about different probability distributions, and then after the long break, we are going to talk about random variables in interaction, which is more interesting, which is related to independence and conditional probabilities. And throughout, I'm going to throw in a few statistical applications. Okay. What's the difference between a random variable and a deterministic variable? You see in maths in general, or maybe in scientific descriptions, we've got we use symbols, right, to denote something. So we can use X for the temperature on for the temperature or for anything. When we use formulas, we use these kinds of variables. And random variable is just the idea that this itself is not a fixed number, but can be random in a sense that can be made more precise than what we will do in this course. So in this course, we are going to stick to the intuitive idea that something can be random, so depending on chance, and that it will be different somehow. I hope this helps. Does it answer the question? Okay, so I would say let's resume at 1:15. Yeah, so we have only got 4 hours. There's only so much we can discuss, but we will discuss the foundations, let's say, or put you in a good spot to read more for yourself, let's say. Okay. Please do reach out afterwards if you've got more questions or if you got other questions. Yeah. Okay. Oh wow, we've got 118 participants. Okay. Okay, so let's continue. So what we've done so far is we've seen a little bit of, let me actually do this like that. Recall what we did, right? We saw a few examples, but we had a few important terms. So we had the term experiment. Remember, that's something random that we want to think about. We had the term random variable. That is typically a number that can be random as opposed to deterministic. So what we usually do in mathematics, I mean, in non-random, non-probability related mathematics, we can have variables that stand for all kinds of things, but which are not random. So we are talking about random variables. And then we've talked about probability distributions. A probability distribution or a probability, actually, if you see this in the literature, there's different ways of referring to it. It can be a probability law, or sometimes a probability measure. And these are assignments of probability values to the outcomes, right? So heads has probability 1/2, tails has probability 1/2. That's a probability distribution. Okay, and yeah, so we haven't really talked about interpretation. We're not going to talk a lot about interpretation, but we are going to have at least one slide on interpretation. There's two main interpretations of probability, right? So until now, I just said, okay, we associate numbers to these outcomes, and these numbers satisfy certain rules. So if you add them all together, there's going to be 1, and these numbers can't be negative and they can't be bigger than 1. Okay, so that's what we have until now. Now we are going to go a little bit philosophical and say, what do these numbers actually mean? Of course, you do have a certain feeling about it, right? If the numbers are smaller, then somehow this outcome is less likely as when the number would be bigger. But one important thing about this is the following idea, which is the frequentist interpretation of probability. And this means, okay, how should you think about p equal to 0.2? or P equal to 20%. So the frequentist interpretation says that if we can repeat the experiment many times, so if the experiment is repeated many times, so let's say n times, okay, we take the coin, we throw it a large number of times, and we take averages, or we throw the die and we take averages of the outcomes, or we count the number of times we get a head and the number of times we get a tail, and we look at how many tails or how many heads we get, relatively speaking, to the whole number of coin tosses that we perform. Right? In this situation, the relative frequency of any outcome x will approach P of x. So that's the number that the probability distribution associates to this outcome, remember? In the limit as n, the number of trials, the number of times we repeat the experiment, goes to infinity. Yeah, actually I prepared something. Let's do it. So share the screen. Okay, that's a Jupyter notebook. Yes. Okay, so you can have this code later, right? We're not going to really go into the details of the code, but what is interesting, of course, is that these experiments you can perform on the computer, so you can have the computer draw random numbers, essentially. And this is mainly to do a little bit of a repetition of the terminology that we've been introducing. So this function here, flip coin, now we get heads, right? Okay, I can run the cell again. Oh, heads again. Heads again. Huh? Oh, now we got tails. So I was worrying the code is wrong. Okay, you see, this is a random variable in our context, right? To make it concrete. Because this really depends on chance. And if I run the code again, we might get a different outcome. Okay, heads and tails. That's a random variable. What's the probability distribution? The probability distribution is the probability that gets assigned to tails and heads. And here in the coin example, this is characterized by this number 0.5, which is the probability, I think, for heads. For example, if I do it like this, with a probability 0.1 for the heads, then we see a lot more tails now, right? So I've changed the probability distribution. Okay, it's not very surprising. This is just to reinforce the terminology. And in this experiment, we can flip the number, a coin, let's say 1,000 times. let's say the probability of getting heads is 0.5. So you see here we flip them 1,000 times and we get almost the same number of heads as tails, but somehow we get a little bit more heads than tails, right? But what happens is that if we take a higher number here, then the relative frequency should approach the theoretical probability. Maybe I will take less here, so if we just take only 10. Okay, so if we take only 10 number of times we flip the coin, then the relative frequencies between heads and tails can be different, right? So here we get 4 tails, 4 heads. But if we increase the number of times we flip the coins, then we should approach the true probability. Okay, so I've already now used the words true probability and showed you this experiment. The way to think about it is that the probability distribution is something theoretical sitting in the background that describes the essence of an experiment. For example, when I say p is equal to 0.5, then it describes essentially the fact that the coin is symmetric and that both sides of the coin are therefore equally likely to be observed, right? The fact about randomness is, of course, that it is random. So if we toss the coin only a number of times, maybe 5 times, then different things can happen. But according to the frequentist view on probability, we can get to the theoretical probability in the limit when the number of trials gets very large. Let me check the chat. Is that random? Is that really random or pseudo-random? Is it possible to have this notebook? So I'm going to first answer, is it possible to have this notebook? Yeah, it's going to be possible. We are going to upload it to the course webpage after, I guess, today in the afternoon, maybe. And the other question is also amazing. So indeed, this is pseudo-random in this case, because yeah, so we didn't really discuss, as I said, philosophical underpinnings of randomness a lot, but in such computer codes, we usually use pseudo-random number generators. So this means this is a piece of code which you don't look at because somebody else developed it and you just call it, and it performs very complicated calculations using, for example, a specific date and number of seconds as inputs, and gives out a number which is not in fact random because it's just the output of a calculation, but the calculation is so random and so unpredictable that in fact it has all the properties essentially of a random number. Yeah, this is a huge topic to discuss further. There are random number generators that are indeed really random using quantum uncertainty, where really randomness plays a role, but in this code, or in general, we use pseudo random numbers. Does this answer the question? I guess there's not so much time to go into it in a lot of detail, but it's a very interesting topic. Okay. Are there other questions? Okay, then let's go back. So we can have the same for the dice. I'm going to somehow keep it keep it like this. So we can roll a dice. You can see here the relative frequencies. They are not exactly all 1/6. They are a little bit different. But this is again due to chance, right? If I take the number here very big, then this is already much closer to being equally distributed. Okay. Okay, yes. Do I do now? Go back. Okay. Okay. So maybe let me summarize what we just said. Random number generator. So just so that you can look at the notes later. Simulation shows the following points. Random number, so that's actually a pseudo random number generator. Number generator in Python or in any other computing language, right? To run experiments, don't need to throw the dice 1,000 times by yourself. And what is interesting again to stress is the relationship to histograms. In particular, theory versus practice. Think about the probability distribution as something theoretical, which is approached in the long time limit or in the limit as we take very many experiments. Yeah, so probability distribution, oops, okay. Probability distribution, that's a theoretical object. Describing the essence, right, of a phenomenon. And okay, and then we can look at histograms. They should roughly look like the probability distribution approaches the probability distribution as the number of experiments goes to infinity. And this has got something to do with observed data. Sometimes it's called the realization of the random variable. So sometimes we say, X is the theoretical random variable. And then if we call the random number generator in a Python script, then this will return a realization of the random variable, or it will return a sample. Okay. And in general, if we do probability, then that often means we put the probability distribution first. So the main object is the probability distribution. And then we think about what can a histogram look like. Okay, the histogram will, I should have put this here. The histogram exhibits fluctuations, right? Exhibits randomness and fluctuations. And probability theory is a lot about understanding these fluctuations or this randomness in the histogram. So that's probability. And statistics, in some sense, is the other way around. Right? So you collect some data that can be thought of as you get the data from the real world. So you think it's some sample or some realization from an underlying true distribution, from some underlying truth, and you try to analyze it and understand something about the probability distribution that lies in the background and that you want to understand theoretically. Okay. Isn't the graph we've just seen for flipping the coin a bar graph, or is it a histogram? I think bar graph and histogram is kind of the same. I think these are synonymous. At least I wouldn't make a huge distinction between these concepts. Yeah, thank you so much for the question. Are there any other questions? Okay. Okay, so this was the frequentist interpretation of probability. Right, frequentist, you hear it in the word, it has to do with relative frequencies, long run averages. Sometimes it's not possible to repeat an experiment, right? When I say something like, the chance of rain tomorrow is 30%, maybe it's not really possible to repeat this, right? Or the chance that my mom had a coffee on the day of a wedding is 95%. That's maybe not an experiment in the sense that it can be repeated many times. Or when I say again, the chance of rain tomorrow is 30%. So let's write down. Chance of rain tomorrow is 30%. That's not really repeatable. I'm going to make this with my mom, right? The chance that my mom had a coffee on the day of a wedding is 95%. So these are things that can't really easily be repeated, and they are typically interpreted in a Bayesian way. So Bayesian, Bayes, after Thomas Bayes, English statistician, and he said, probability quantifies a degree of belief. So I just kind of think that this is true. So there's some subjectivism in this idea. There's also different variations of Bayesian interpretations. This can be both subjective and objective. There's slightly complicated and subtle discussions about this. But it's good if you've heard it, because these two interpretations of probability, although they might seem a little bit lofty or subtle, this distinction is quite important in statistics, especially nowadays, because if you adopt one of these two standpoints, this suggests different ways of performing statistics, or maybe said more broadly, these two different schools of thought about probability lead to different paradigms and different procedures, algorithms, even research communities. Okay. Not sure we can discuss the statistics of this in great detail today, but it's interesting to have heard about it. Okay. Okay. 3, 4 new messages. Okay. There's good comments on random numbers. It's very nice. Thank you so much for helping with this. Okay. Other questions? We are going to start a new topic. So become a little bit more hands-on, maybe, doing actual calculations. So remember, we had random variables, we had probability distributions. Okay, these are the main concepts. We had experiments. So these 3 terms, try to keep them in your mind. Now, next, of course, what can we do now, right? What can we do? With random variables? Probability distributions. Okay, something has to be calculated, I guess, at some point. And so let's maybe focus again. So in this section, we are going to focus on the die, right? So we can make a little table like this. So, okay, recall the random variable that we've been talking about is like this: 1, 2, 3, 4, 5, 6. Okay, that's the random variable. First line. Second line, probability distribution. We said if the die is fair, if it's unbiased or unloaded, then all of the outcomes occur with equal probability. And since they all sum up to 1, this has to be 1/6. And we can also consider, so that's a unbiased die. Okay, but we can also have a different kind of die, which is unfair, right? Or which is a little bit dodgy. So maybe it's much more likely to get a 1, for example. Okay. What do I have to have here? It has to sum up to 1, right? So 0.6 plus 0.1 plus 0.1, that's 0.8. Then plus this, plus this. that's going to be 0.9. So I have to make it up until 1. So we have to put 0.1. Okay, let's say it's a dodgy die. Okay, right? So we've got the random variable here. We've got two different probability distributions. And okay, we're going to discuss three things now. First is we can lump together outcomes. So that means maybe we are interested in even numbers. Okay. And so such a lump, this is called an event. Yeah, this is a new term. So we had the terms random variable, probability distribution. Then we had outcomes. Outcomes are sort of oops. Outcomes are sometimes also called elementary events. So we can have other events. For example, elementary events. Which are really just the outcomes themselves, right? Or we can have something like smaller than 4. Okay. So that's an event. An event, we could be more precise. We could say that, okay, an event is a subset of the sample space, but we don't really need it that much. So we can have a certain event, whole sample space, okay? Yeah, what do we do with it? We're going to have our first rule for calculating with probabilities, and it's going to be called the sum rule of probability. And this rule answers the following question: how do we calculate the probability of events, right? Before, we only had probability associated to outcomes or to elementary events, and essentially this was just an assignment. Now, starting with these assignments, remember the big question about this section is, what can we do with these probability distributions? And we ask the question, how do we calculate the probability of events? So that means, how do we calculate the probability of outcomes that are lumped together? And the rule is just we sum it together, right? We say the probability of outcome is even. So that's just notation. The probability of 2, 4, 6 Okay, now we do the sum, P of 2 plus P of 4 plus P of 6. Now notice that depends on the probability distribution that we're talking about, right? If we're talking about the unbiased die, then this is going to be 1 over 6 plus 1 over 6 plus 1 over 6. So 1/2, 50%. Okay, for the fair dice, for the fair die. If we have the dodgy die, then it's different because the probability distribution that underlies this calculation is different. So we can do a calculation like this. Often we write something like this because the probability depends on which die we use, right? Dodgy die. So the outcome is even. But again, the same rule applies. Okay, now we can look it up in the table. I've already looked it up in the table. So we look at this table. So for even, we need 0.1, 0.05, and 0.1. Okay, yes, so it's different. I think this is quite intuitive, but it's important to be careful with this rule. So let's make a warning. Is there a question? No question. Whenever you use the sum rule, you should be quite careful. So for example, that's the last thing we're going to discuss before the break. Suppose you conduct a study on healthy lifestyle, right? And you look at different people and you record whether they exercise regularly. So you record whether people exercise regularly. Let's say that's event 1, right? So before we were thinking about events as lumping together outcomes, but an event in a more abstract or in a more abstract situation where it's not so clear what the sample space actually is and so on, we can still think about events in terms of sentences, for example, right? So this would be event 1. Or whether they eat a balanced diet, right? Let's say we call this exercise regularly. And here, balanced diet, BD. And we can think, okay, maybe in the whole population, there's a certain percentage of people who exercise regularly and a certain percentage of people who eat a balanced diet. So we could, for example, write something like the probability that a randomly chosen person in the population or from people you encounter on the street, for example, exercise regularly, let's say is 0.6, 60%. I'm not sure it's true, but let's assume it is true. Okay, eat a balanced diet. %, let's say. Okay. Now let's say you want to calculate the probability that somebody exercises regularly or eats a balanced diet. Okay, when you encounter somebody, and then you can say, we use the sum rule of probability, so we do 60% plus 70%. %130%. Okay, so now you see something has gone wrong, right? Because it can't really be bigger than 100%. So it's actually can't calculate like this. What has gone wrong though, right? What's the problem here? So that's important. The sum rule can only be used if the outcomes or the events that are added are mutually exclusive. So that's very important. The sum rule can only be used if the outcomes events that are added are mutually exclusive. Okay, so what does it mean? Think back to the die. With a die, getting a 2 or getting a 3, these are two mutually exclusive events, right? Because on the die you can't see two different numbers at the same time, let's say, right? Of course here that's not true. So a person can exercise regularly and eat a balanced diet. So that's possible in one person. And so these two events are not mutually exclusive. And that's why the sum rule can't be used. Okay, I think it's time for a break. We are going to discuss this a little bit more after the break. We are going to recall this a little bit, and then we are going to move on to other things that we can compute from probability distributions. Yes, subtract the intersection between ER and BD. Exactly. We are going to discuss this a little bit after the break. And then we are going to move on to mean and variance and continuous random variables. Are there any questions now? Is it too slow? Is it too fast? Is it okay? Okay. Is the frequentist interpretation related to the central limit theorem? A little bit. We're going to hopefully, I need to speed up. We're going to hopefully discuss the central limit theorem. Okay, I could go a bit faster. Okay, then let's do it like this. You have a little break. You have a coffee and maybe a little snack, and we're going to resume in 20 minutes. So the frequentist interpretation is more related to the law of large numbers. The law of large numbers means that, have I mentioned this? The law of large numbers means that in the long run, when probabilities settle down, we are going to have we are going to recover the true probability, and the central limit theorem says a little bit more about the fluctuation. It is a little bit more precise in this way. Okay. Yeah, then I'm going to see you in like 20-25 minutes. Okay, then there's some other questions. Okay. Okay. Okay, you bite. I don't know if I pronounced this correctly, but I'm going to answer it later. Thank you so much for listening so far.
So red with an orange, Julius? Hell no, let's do it. Trev, your nose is bleeding.
Okay, can you hear me? Okay, perfect. Okay, ladies and gentlemen, welcome back to the lecture on introductory probability and statistics. Before the break, we had discussed a case where it's not possible to use the sum rule for probability. Sum rule and probability, we just added these two probabilities to find something that's not allowed, right? Bigger than 100%. But this could also happen if the probabilities are small, right? It could be like 2% here, 3% here. And in this case, it's really dangerous because we might not notice that there's a problem because we do not exceed the 100%. So therefore, it's important to take this warning seriously and to really think about basically whenever you see a calculation in a probabilistic or statistical context that uses a plus essentially, then think about whether really these two events are mutually exclusive. So here, mutually exclusive was the keyword. And okay, we already had said that sorry. Getting two different numbers two different numbers on a die is mutually exclusive, we can only have one of them, or we can have at most one of them, whereas it is perfectly possible for a person to exercise regularly and also to eat a healthy diet, right? So that's possible. Okay. In contrast, one person can both, right? So this both, of course, goes against the idea of mutual exclusivity. Exercise regularly and so this was event one. And eat a balanced diet. That's what we called it. Okay, event two. Great. So then there was a comment in the chat that this actually can be to some extent mitigated. So think about this. And this is an introduction to a sort of a geometric view on probability, right? You might have seen these kind of diagrams that we are about to draw. So let's say here we've got the event exercise regularly. And then we had the other event, balanced diet. And so in fact, we said these two events were not mutually exclusive, but there was some sort of overlap, right? There are people who only exercise regularly but don't eat a balanced diet. There are people who do the other way, who eat a balanced diet but don't exercise regularly, and there are people who don't do any of these two things. But there are also people who do both things. And so the geometric way of thinking about it would be like this. So we would have some overlap here. And so this connects probability both to this kind of geometrical intuition and also to logic. So maybe we can take a new color here. Okay. So this would be BD and ER. Okay, and we can also talk about OR. So let's say, if we think about these two shapes joined together, so we would say that's the union of the two events. Okay, so notice these logical conjunctives. Important here to notice this is an inclusive OR. So that means this means it's not exclusive, right? We are talking about people who do either ER or BD or both of them. and we don't exclude those that do both of them. Okay. Okay, so on a high level, we can say that such diagrams allow us to think about probability as some sort of area or volume associated to sets. So we didn't really talk about sets because it takes us a long time and it's more on the foundation side, and you can read it up for yourself. But basically a set in this picture is just one of these bubbles or a certain region that we drew in the picture. Or we can think of probability as some sort of substance distributed in some space. Okay. So in particular, we can now repair what we had done wrong before. So we can now write the probability that the person exercises regularly, or, so this is just notation. I know that this part is a little bit fast. I'm trying to go a little bit fast in this part so that we've got a little bit more time to discuss other more statistical and applied data science issues later on. But I'm just sort of making you aware, I hope, of some of the notation and of some of the ideas in the field, and then you can read more about it by yourself. So remember, we had this sum rule that we used before to compute probabilities of events. Now, we saw that with the sum rule, we have to be really, really careful whenever the events are not mutually exclusive, such in this case. Right? Remember this problem over here. Now we basically are going to repeat this formula, but we are going to mitigate this problem. So we are going to have something else here. And if you look at the picture here, what are we trying to do? Right, we are trying to compute the probability that a person exercises regularly and eats a healthy diet. So that's the notation for or sometimes that's the notation for union. So whether or not if you think about set theory, you would call it a union. If you think about logic, you would call it or you would maybe write it like this. These are essentially the same things. It's just that this is more of a logical symbol. Where this is a set theoretic symbol, but essentially these are the same things. And so this means we are trying to compute the probability, or if we want to think in geometric terms, we are trying to compute the area associated to this region, and this region is built from ER and BD by taking both together. Taking both together is this symbol. And so we're interested in, so that's ER, that's BD. Taking both together would be this. And so if we write down what we had before, so we said, okay, that's the probability of BR plus the probability of BD. Remember, we had a problem with the sum rule. Where's the problem? If we add this area to this area, then this area here in the middle is counted twice, right? So again, we add this to this. This is counted twice. So that's the problem. And we only want to count it once, right, to compute the whole area. And so we need to subtract it. So the formula is this. So this is logical AND. And if you want to think in terms of geometry, that's or some sort of graphical illustration, that's the intersection or the overlap. Okay. Yeah, so this formula corrects the sum rule by introducing this additional term. And in particular, if we did this here, so we would have to put something in here, then we would get below 100% here. Yeah, unfortunately, we can't really complete this example here and now at this point, because we don't really know what the probability is that a person does both, right? So it's not given in this exercise, in the statements here, and so that's all we can do at this point. We're going to think about these questions more in the part 2, right? Because that's really about interacting random variables, and the interaction precisely happens at this point here where there's overlap. We're going to discuss these types of overlaps a little bit more in the second part. Okay. Yeah, this was maybe a little bit fast, but we're going to come back to it in part 2. Are there any questions about this? Okay, no questions in the chat. We're moving ahead slightly. So remember, we discussed the main players, random variables and probability distributions. And we were discussing, okay, if we've got a probability distribution, what can we do with it? And the first thing that we discussed was lumping together outcomes to events and computing the probabilities of these events. Now we are going to discuss mean and variance. Oops. So these are numbers, in the simplest case, that we can use to describe a probability distribution. These are also concepts that are useful to analyze data. When you get, for example, you can download data from the internet, or you get data in an applied context while doing a project, then these would be good things to look at. Okay, so what is it? Let's think back to the dice. So I'm just going to copy it. Okay. Again, remember we've got our random variable. We've got our two different probability distributions, unbiased and biased, or dodgy. And we are now going to say the mean. That's what we are going to discuss. The mean has different names. So we can also say sometimes it's called the expectation. Sometimes it's called the expected value. What is it? Let's make a definition. Is a weighted average over the possible outcomes Okay, often this is called mu, Greek letter mu, or we write an E like this, where x is the random variable. So remember this x is here. This is really just notation, right? Nothing happened in this equation. It's just a different way of writing the same thing. And now comes the definition. Okay. Okay, I am aware this involves maybe complicated notation, so let's unpack it. What does it mean in this example? So the sum notation means we have x1 times, so the outcome x1 times the probability that x1 occurs, plus the outcome x2 times the probability that x2 occurs, and so on. Okay, so essentially these dots over here, they correspond to the sum sign over here. Yeah. Okay, so this is a more compact notation for this. In this example, let's do this example. For the unbiased die. Okay, so what we are calculating here, the expectation or the mean, this will depend on the probability distribution that underlies it. So sometimes this is indicated here as a subscript to the E. So let's do it. That would be 1, right? So this x1, the outcome x1 would be 1 times the probability, that would be 1 over 6. The second one, the second output is 2 times the probability that x2 occurs, so that would be again 1 over 6. Okay, since in the unbiased case all outcomes are equally likely, this will end up looking like that. Okay, and this is going to be 3.5. Okay. What does it mean in words? The average outcome is 3.5. And yeah, so it is a way, there's different ways of thinking about this, right? You can think of it different ways of thinking about it. If you think geometrically as a histogram, then the mean characterizes the center of the distribution. Think of our experiment. We had something that looked like this. So there was 1, 2, 3, 4, 5, 6. In this case, everything was equally likely, and the mean was here, right? So we calculated that this is the mean. And as you can see, that's in the center of the distribution. Okay. We also had, so that's an unbiased die. We also looked at a different probability distribution. There we had more probability on the outcome 1. It looked more like this. Maybe do the calculation as an exercise, right? So the calculation would be using this formula, using these values, or using a calculation like this, but using different numbers here as prescribed here in the table. Okay, so you would find that the mean is shifted towards here slightly. Okay, and this is because the weight of the distribution in some sense is shifted towards the left, so in this direction, because of the prevalence of, so because of how likely the one here is. Okay, dodgy dice. So as such, note that there is some reduction in complexity or reduction in the information content, right? So here in this table, we had the whole probability distribution. And now we've reduced this probability distribution to one number that, however, says a little bit about the probability distribution that we're looking at, right? So this is interesting for data analysis because that's what a lot of data analysis is essentially about. So getting a lot of data, looking at the distribution, maybe looking at histograms, and then getting some interpretable information out of it. So that's our first example of this, computing the mean from a probability distribution. Let me check the chat. Okay, no questions, I think. Okay, so that's a geometric interpretation. We've also got a frequentist interpretation. So that was a geometric interpretation. Frequentist interpretation. And this would be the law of large numbers. That we've seen before. Okay. What does the law of large numbers say? Remember what we had said about the relationship between the probability distribution and the histograms. So, or the bar charts, right? We said that if we repeat the experiment, then in the long run, the bar chart or the histogram will approach the probability distribution. It's the same here for averages and the mean. Let me write it down. Again, frequentist means we repeat the experiment. If we repeat the experiment, the same experiment, a large number of times, then the average over the outcomes will approach the expected value or the mean. So that means we throw the dice once, maybe we get a 1. Second time we throw it, we get a 4. So let's calculate 1 plus 4, then over 2, right? So the average between the first two rolls, 1 plus 4 over 2, that's 2.5. That's the average from the first two rolls. Then we take the die again, roll it a third time, and compute the average over the first 3 rolls, and so on and so forth. And if we do this for a long time, then we expect to see 3.5 in the limit. Actually, there is a little experiment. Let's do it. So that's our law of large number experiment. Of course, you can have the code later. What's happening is here we're not doing it with a die, we're doing it with a coin, but it's the same principle. Here the coin is fair, so we've got 0.5, and we assign to heads the value of 1 and to tails a value of 0. And so if we take the expected value, then that's going to be 1/2. It's 1 times 1/2 plus 0 times 1/2. That's going to be 1/2. And in this plot, you can see what I just described before. On the x-axis here, we've got the number of tosses. So we start with few tosses and compute the average. And here we've got 1,000 tosses and compute the average. And as you can see, if we do this for a long time, we should approach the value 0.5. What happens if we change the probability of heads? Maybe 0.8, do a biased coin. This will change the expected value, but the law of large numbers still applies, right? So as we go in this direction, so towards a higher number of coin tosses, the average over the outcomes will approach the theoretical value. So it's very similar to what we had before, where the histograms or the bar charts approached the theoretical probability distribution. In the same sense, the expected value is something theoretical, and the average is something that we can observe or compute from data, or that happens in the real world. Okay. Are there any questions about this? Sorry, I kind of missed the... Where's the chat? Ah. Any questions about the mean? Okay. If there are no questions about the mean, yeah, in the interest of time, I will go ahead and how's the design of this chart set using the codes? I'm not sure I understand the question, unfortunately. Are you asking about like how the Python code works, or? Yeah, so this Python code uses different packages. So there's the package random that can produce random numbers, and there's plotting packages, and you can use these. I would say we can probably discuss it after the course, because we don't have, unfortunately, enough time to get into the details of the code. But the code will be online on the webpage, and then you can have a look and also ask questions. Okay. Sorry about this answer. It's a little bit unsatisfactory, maybe, but what can you do? We're going to discuss next variance and standard deviation. Okay, so remember we had a way of characterizing probability distribution of characterizing probability distributions by the mean. And doing this, we had some loss of information, right? For example, we had a distribution that looked like this. Okay, and the mean could be maybe somewhere here. Remember, the mean says something about the center of the distribution. Okay. That's the first one. Ah, sorry, I need to share it back, right? Thank you for... Yeah. Thank you so much for letting me know. Can you see it now? I think it should work.
Yes, we can see it.
Okay, perfect. Thank you. Okay, so we had this red probability distribution over here, which was kind of a complicated object. We computed the mean, and that's our summary statistic for this distribution, right? So we lose information, And the fact that we lose information, you can see that if we have another distribution, it can have a different distribution. It can be a different distribution, but it can have the same mean. So for example, it could look somehow like this. Okay. Also in this case, the mean might be here. Remember our geometrical intuition, right? The mean somehow characterizes the center of the distribution. In both cases, the center of the distribution is maybe here at the same, is the same number. But we would like to say something like that this distribution in some sense is more spread out, whereas this distribution is more concentrated around the mean. And so this connects to a very nice question from before. So we said that there was a question, can you say something about how random an experiment is? So we would like to say something like, this is quite random, this experiment. And this experiment is not as random as this, right? So the first experiment or the first distribution is not as random as the second distribution. If we take it to the extreme, we could have a distribution that looks like this. Okay, this would also have the same mean. And in this sense, somehow there is no randomness at all, right? Because if the dice is like this, we would always get the same outcome. So in this sense, this would be least random. Or not random at all. And this would be the most random, right? In comparison to the other two. Let's say more random than than 1. Okay. So that's interesting. We are looking for a way of okay, so we would like to describe this in mathematical terms. And you probably already kind of know or suspect that this has got something to do with variance. So the variance we say something like, let's write something like this. One is spread out is concentrated. Okay. Yeah. How can we characterize this or describe this in mathematical terms? Okay. So the key concept is the concept of variance. And we write the variance of the random variable. This is now a definition. So the definition is built on the concept of expected value. It builds the expected values together. Okay, so this looks complicated. What does it mean? So in words, the variance is the expected, so expected, think about average, deviation, squared deviation, from the mean. So look at this formula. Here, this is the mean, and x minus the mean. This kind of tells us something about where we are in comparison to the mean. So if we think back about these pictures, that's the mean, and we are thinking about deviations from the mean. That is about distances, for example, from here to here, or about here to here. And we are trying to make a statement about how likely these are going to occur in the experiment. In this example, there's no deviation at all happening from the mean, because all of the outcomes are actually centered on the mean. If we compare the first and the second experiment, then the deviations from the mean in the first experiment do happen, but they happen with relatively low probability, right? So these probabilities are smaller than those probabilities. And that's precisely what we are trying to say in this definition of variance. It will become a little bit clearer when we unpack this formula. So this formula I basically wrote because you will see it often in books. But if we want to make a calculation with it, then we should expand it or unpack it. Actually, it's also helpful to understand its meaning. So we write something like okay, the first expectation here, remember how it was defined before? Here we said whenever we have got an E like this, we replace it by a sum and we sum over the outcomes. So this x corresponds to this x, and we take into account the probabilities. We're going to do the same here. Let me first write the formula and then I'm going to explain again. So the first E is replaced by a sum. Then we've got the probabilities. And now before we had, here we only had x, and then we wrote xi. Now we've got this more complicated expression. So the xi have to be replaced by this more complicated expression. It looks like this. Oops. So you see, again, these are the deviations. Deviations from the mean. And this is a weighting how probable are these deviations? Okay. Let's illustrate this formula. Again, if you're uncomfortable with the sum is a way to compactly write down a sum of a number of terms. So let's calculate it for the unbiased die. Okay, so we start here again. We've got these i's. I means it runs over the outcomes. So the first outcome has probability 1/6. The first outcome is 1. And the mean, as we calculated above, is 3.5. Okay, so the deviation of the first outcome from the mean is 2.5. And then we square it because of the formula. Okay. The same happens for the rest of the outcomes. So we've got the outcome 2, which deviates from 3.5 by 1.5, and so on. Okay, you can take a calculator, make the calculation, and you will see that this is approximately 2.9167. Okay. Okay, this is a measure for the variability, right? So for the randomness, inherent in throwing an unbiased die. Okay, one more thing maybe. You might have wondered about these squares over here. If we didn't have them, then these contributions to the variance might cancel. So we might get a negative number here and a positive number here. So if you look at these pictures, a deviation like this might count negative, a deviation like this might count positive, and then in the end, if we just sum these numbers up, we get cancellations. So that's not really what we want. We want to really count this and then add together this. And that's why it's a good idea to square these numbers so that they can't cancel out. Yeah, summing up, we've now looked at two numbers that can be associated to probability distributions. So one of them is the mean, one of them is the variance. And the mean corresponds to the center of the distribution, and the variance tells us something about the way the distribution spreads around the mean. And there are some other measures for variability, but I think I will jump over this. One important thing, since we're doing data science, is how to estimate mean and variance from data. But before I discuss this, are there any questions? Or is it clear? Is there a difference between standard deviation and variance? So I thought I would skip this, but the standard deviation is another measure for the variance, or for the spread of the distribution. And you get it by just taking the square root of the variance. Sometimes, exactly, there's another question. What exactly does 2.9167 signify? That's one of the criticisms that you might have when using the variance. It doesn't really immediately signify anything. The standard deviation is a little bit more interpretable. In particular, so if you look at the variance, if we think about probability distributions that have units, so for example, if we are measuring height of people, then we think of, maybe we measure the height in centimeters, and if we compute the variance like this, then there will be centimeters squared, right? So we have a centimeter here, and then we square it, so the unit will be centimeters squared. That's a bit weird. If we take the standard deviation, if we take the square root, then the units will be in centimeters. So the units of the standard deviation are the same as the units of the random variable that we're interested in. And this might be better. I will come back to this hopefully in like 20 minutes, where we can get a better interpretation yet of the standard deviation. Okay, but thank you so much for the question. I think I need 2 minutes of break for drinking a little bit of water. My voice is struggling. Okay. Yeah, thank you so much for the questions. Great questions. One important thing is that we can estimate the mean and the variance from data. I will just write down the formulas because they look very similar to the formulas we had before. It's important just for you to know that it is possible. If you have data, then you can estimate the mean and the variance from it using these formulas. And usually you can look these formulas up, or you use a Python command for it. The formula here is very similar. It's just that instead of the probabilities, we have used we use 1 over n. So this is like saying that the data, so this is like attaching equal weights of probability to the data points. Okay. Right, and a similar formula. So this hat, this is just notation, this hat the hat indicates that this is something which comes from data. It's an estimate, okay? In statistics, this is a very common notation. Okay, and similarly for oh, that's a bit extreme. Mean from data. Variance from data, okay? So these are the data points. Okay. Okay, it is a little bit rushed. I thought I would be a little bit quicker, but yeah, let's discuss continuous random variables a little bit. We need to discuss Gaussian random variables a little bit, which is a continuous distribution. So until here, we had talked about discrete random variables. So the dice could be 1, 2, 3, 4, 5, 6. And now we are going to talk about continuous random variables. Most of the concepts will generalize pretty much straight away from discrete random variables. But there will be some important differences, right? Recall continuous random variables can attain any value in a specified range or interval, right? So we've got, in general, infinitely many outcomes of a random variable. And you should think about measuring the height of a person, for example, or measuring the temperature, or time to complete a task, something like this. Right, so these outcomes are typically continuous. Remember, we had two key concepts. We had random variables and probability distributions. the concept of random variable doesn't really need to be changed at all. But the concept of probability distribution, or the description of this probability distribution, needs to be changed a little bit. So random variables check. Probability distribution let's start with an example. Let's say we measure the height of a random person, right? The height of a random person that we might encounter on the street or somewhere. So we had histograms and things like this before. You might imagine that now it looks a little bit different. So it could look like this. Maybe the most likely height is 1 meter 80. And then the distribution could look somehow like that. So it's considerably less likely that a person is much smaller than 180 or much taller than 180. And so we think of this in terms of a function, p of x, which is called, that's an important concept, probability density function. Or PDF. Okay, this is quite similar to the probability distributions that we had before. So before, this is quite similar to, remember this, the p of heads is 1/2, p of tails is 1/2. Right, so it serves a different purpose, and it has a few similar properties. For example, this always has to be bigger or equal than 0, so probabilities are non-negative. And higher values of p of x indicate, this is a little bit, needs to be made more precise maybe in the following, indicate that the outcome x is more likely. And then another important similarity is, remember here we had the fact that probabilities sum to 1, so p of heads plus p of tails, this was 1. And when we go from a discrete setting to a continuous setting, then often sums are just replaced by integrals. So we had, so this would mean if we integrate instead of sum over everything, remember your calculus lecture, okay, this is the equivalent or the analogous statement. So this is the analogous statement to this statement. And mean and variance are also defined in a similar way. Okay, we just replace sums by integrals. Okay. Okay, these are the similarities. What are the differences? So when do we need to be careful when working with continuous random variables? We've got a warning in place. And the warning is related to the following question. Imagine somebody asks, what is the probability that a randomly chosen person's height is 180? Okay. If we look back at this picture here, at this graph, the temptation is really to just look at 180 and try and read this off, right? So that's the temptation to do it. And it's important to remember and realize that that's wrong. So why is it wrong? So the temptation is just to read this off. But it can happen that actually this value is bigger than 1. Okay, so again, this is not really allowed. There has to be some kind of problem there. Okay, the problem is really the problem is really with the way the question is asked or the way it is interpreted. If we interpret this question literally, then, so that's the question. The answer to this question would be if we take this question literally, the answer is 0. Okay, why is this? Because if we ask the question in this form, then really 180 is the same as 1.800000000, right? And this is different for example, from okay, so when the question is asked in this way, it really means that the person measures 180 extremely accurately, and the chance that this really happens and there is no deviation at all is in fact 0. So this is of course not very satisfying, and therefore a better way of asking or interpreting this question and in fact a better way of working with continuous random variables, or this is the way you have to work with continuous random variables, is what is the probability that the random person's height is approximately 180. And the emphasis here really is on the word approximately. And we need to ask the question somehow in a softer way. So we could, for example, say between (1.795) and 1.805. Okay, so this is linked to the fact that actually it doesn't really make sense, maybe in an absolute sense, to say somebody measures 180 because the measurement device, like a ruler, it also has only a finite accuracy, right? So we can only measure some person's height up to some finite accuracy. So it is linked to the finite accuracy of measurement devices. Okay, and then using this reformulation, we can in fact compute something. So if you think back to this picture, then now instead of looking just at this 180 over here, we construct a little interval around it, and we ask about the area that is enclosed by the curve and this interval. Okay, so the answer to the question then would be the probability that the random variable x, right? Remember the name random variable, is between these two values, can be calculated using an integral like that. Okay. This integral might, of course, be difficult to compute. Back in the day, you would use maybe tables, depending on the distribution. that you were interested in, but nowadays you use a computing language. So Python will have comments for this. Okay, I'm reading the chat. Sorry, I missed quite a few questions. Sorry about that. Let me answer them now. So one question is, sorry, what do you mean by from data? Isn't the previous calculation also done from the same set of data? So there's a little bit sometimes a subtle distinction between thinking about a probability distribution and thinking about data. So the probability distribution is a theoretical object that we impose, that we think describes the essence of a phenomenon, and that we use for a description, for example, in a physical law. And if we use data, we can get this, for example, from observations or from a study. This is a little bit different. It is similar to what we had when we looked at the averages versus the expected value, or it was similar to when we had the bar charts or the histograms versus the probability distribution. As we increase the number of data points, these objects, which are somehow more connected to the real world, which contain fluctuations that are not completely so these fluctuations that are contained in the real world data, they will average out if we have enough data points. Is this kind of, I hope this helps in the understanding. I'm happy to answer a little bit more later as well. Why do we subtract 1 from n? That's a very interesting point. So I guess you're talking about this. So this is a little bit of a trick. Actually, 1 over n would also be okay, because this doesn't make a huge difference. So 1 over n and 1 over n minus 1, that's quite similar in terms of the size of this number, and it won't typically make a big difference in data analysis. The reason why 1 over n minus 1 is used is, so it has the theoretical property that it will be unbiased. I don't think I can explain now what this really means, but it means that essentially it means if you use 1 over n instead of 1 over n minus 1, then on average you will underestimate the variance of the data. So you will you collect data points from the real world. Maybe you collect the heights of people, and if you compute the variance based on these data points using 1 over n, then you will get a value that is slightly too low. So maybe I had a better idea of what I could say about this same set of data. The difference is essentially if we say the height of people is distributed according to some probability distribution, that's a law, or that's an interpretation that we give theoretically to this process. But if we go to the street and collect 100 people and collect the average and compute the average height or the average, or collect the sample variance from these observations, then that's this. Is standard deviation gives a clear idea about how far the values are spreading or deviating from the mean. Okay, that's a good point. I think I'm gonna try and finish this lecture by discussing the most important continuous distribution. The most important continuous distribution is the normal or the Gaussian distribution. Okay, I'm sure you've seen it a number of times. There's two ways of looking at it. So first of all, we've got the formula. And second of all, we've got the picture. Okay, this is a very important distribution. Of course, I think you've seen it a number of times. The most important, so there's a few points about this. The first point is this is a family of distributions. A family of distributions means that it's not only one distribution, but we've got two parameters that we can play with. So it's the sigma and the mu, and they play the role as indicated by the choice of the letters of the mean and the standard deviation. And if we change them, then this picture is going to change. Okay, so we can somehow move this distribution around. It could, for example, if we change mu and sigma, then we could have a distribution that looks like this. So for example, mu tilde and sigma tilde. To repeat what we had seen a little bit before, the role of mu, so the mean, is to determine the center of the distribution. So for example, if mu is 1, this looks like this. And if mu is 2, so this would be mu equals 1. Oops. Mu equals 2 looks like this. And we can have the same analysis about sigma. So sigma can be small. Then the distribution looks like this. Oops. or sigma can be large, then the distribution looks like this. Okay. Yeah, this is very much connected to what we had said before about mean and variance. Why is it important? Why is it so important? And we have time to only discuss it a little bit vaguely, but there is a phenomenon in probability and statistics that this distribution tends to show up whenever the Gaussian or normal distribution, okay, these are synonyms, shows up whenever a quantity can be thought of as originating from a large number of small random influences. So for example, when you think about the height of a person, maybe the height of a person is composed from the influence of many gene expressions, right? Or the time that it takes you to go from one end of the city to the other end of the city. This is a random time which depends on many small influences. So maybe the first traffic light is red or green, the next traffic light is red or green. And the whole time that it takes will depend on very many small influences. So the Gaussian normal distribution shows up whenever a quantity can be thought of as arising from many small influences. Which are independent from each other, right? So maybe the first traffic light and the second traffic light, they are not really correlated, right? So these are independent random events. There have to be many of those. And none of them can be too important. So every one of these little influences is comparatively of little importance. Okay, let's say I have 100 readings of different animals' heights, which is scattered when plotted. So can I convert this data into any distribution as I like? I'm not so sure I understand the question correctly. How many do I have some more minutes to wrap it up, or how should we do it?
Please go ahead. We can, you can use as much time as you need.
Hello? So I probably need to connect the So I'm going to be back in a second. I need to connect to the plug. Ooh. Okay. Okay, sorry for this. Okay, so let's wrap it up what we did. I need to share it again, I guess, right? Okay, so let me maybe summarize what we did. In the second half. So we had the idea of looking at probability distributions and thinking about these probability distributions. And we had looked at the mean and the variance. So you can't really see it, right, what I'm writing? I'm trying to write something on the tablet, but it doesn't really seem to work. Okay, then I'm just going to, you can see it. Yes, until the red line. But I'm trying to write more things. Okay. Okay, so if I can't write more things, I'm going to show you a last experiment. You can see this, the Jupyter notebook, right?
Yes, we can see it.
Okay, so what we did in the second half was now we looked at probability distributions and we looked at ways to describe them. So we had the mean and the variance. The mean is connected to the center and the variance is connected to the spread. So for example, you could download distributions like this that you want to analyze, or that you want to or you have data that you want to analyze in your project, and you could look at the distribution of this form. And now you've got a few tools to reason about it, right? You could say that the mean is somehow here in the middle. So you can see my cursor, right? It's the green. I'm having my cursor on the green histogram, Cauchy histogram. So it's in the middle. the mean is at 0, we can compute the variance or the standard deviation to say something about how much it is spread. And the last thing that I will have to skip now because of time is to think about tail behavior. So we can think about the center, we can think about how much the data is spread around the mean, and then we can think about outliers. And this is kind of important. What I said before is that the Gaussian normal distribution typically arises from the situation where we have got very many little influences that result in a bigger outcome. And none of these little influences is very important. So you might think that this is often the case. It's not always the case. So for example, when you look at at salary distribution or at wealth distribution in the population, or if you look at the size of cities, then you will see that there are far more people with a huge salary or cities with a huge population than would be expected from a normal distribution. And so this then, you can reason about it thinking that maybe the way wealth or salary is determined is not really depending on very many little effects, but there have to be quite a few, maybe only a few factors that are important for this. Okay, and this gives a way to analyze it. We don't have, unfortunately, more time to discuss it in more details. These are so-called QQ plots. And you can see from these plots that these outliers, so if this was a normal distribution that was plotted here, then the blue points would be on the red line. And the fact that here the blue points are significantly above the red line or significantly below the red line signifies that there are a lot of points quite far out, both in this direction or in this direction. And so this is something to be to care about, because many statistical methods are based on the assumption that the underlying distribution is a Gaussian distribution. And in fact, nowadays, many people argue that financial crises are in fact driven by the effect that the people who reason about these probabilities underestimate rare events and outliers, so very small or very big values. Okay, I'm a little bit sorry I can't really explain it in more detail now, or with in a more relaxed way. I'm happy to take on questions or maybe help on later. I'm not really sure what the schedule is. I think we have to end the session now. Are there any other questions? Thank you, sir. Thank you very much for the very nice comment, Lina. Thank you. Thank you. Okay, then thanks everybody for listening. There's another question. Okay, there's another question about Ubyte. So you're saying you're getting rejections in the admission process of data science masters. I'm not so familiar with the data science masters environment. Inferential statistics. If you want, you can send me an email with a link to the data science masters, and I can maybe have a look at it. Because I'm not so sure how to answer.
Nicholas, there was a questions earlier about when using linear regression models, which assumes
So my email is.
And so Mia wants to ask what happens if the data that they have is not normally distributed, and what can they do in such a case?
So in order to use some machine learning models, like a linear regression model, which assumes the data is normally distributed, and I have the data that is not normal in that doesn't obey normal distribution, what to do in such cases? Can I convert the data into a normal distribution? I think there was already an answer. So it's a very difficult question in general. I'm afraid you can't really do anything. It's because if you don't really understand the underlying distribution, then it's difficult, right? There are some more advanced techniques that work, for example, for Cauchy distributions. So these are distributions which have heavy tails. Heavy tails means that there's lots of extremes in the data. You can look at literature for regression, for example, that assumes different distributions from normal distributions. I can maybe, if you write me an email, I can direct you to some of the literature, also answer more questions about it. It's a little bit tough to answer this question in generality. Okay. Let me write this down. Okay.